Good morning.
Good morning, dear colleagues.
Good morning.
Good morning.
Good morning.
So, dear colleagues, let's start or let's continue our session. And today is the third part of the session section, System of Information Security. And due to some obstacles yesterday, some problems was with speaker's connection. So the first speaker for today will be IntelITSIS, please. I'd like to remind that we have about 10 minutes for you to speak, okay? Nicola, are you ready?
I'm ready. Good morning for all. Let's start begin. My turn.
So you have to share your screen and show.
Yes, I'm starting to share my ecran and demonstrate my. Are you seeing my presentation?
Yes, we see. Thank you.
My presentation is a method of the interlice of influence of malware software on the work of client automated workplace specialist. And using scientific task is development of information technology that automatically neutralized the manifestation of malicious software on client workstation of specialized information system. Information system architecture with two-tier system of concentration the effects of malicious software, where you see on the picture. Method of ensuring fault tolerance and survivability of the information system using parametric control of revelations of software modules of client automated workstation. Model of the method of ensuring the fault tolerance and the survivability of information system under the influence of malicious software. Component of technology to ensure fault tolerance and survivability of specialized information system. Schema of interaction between the background process and the program loader program. Software model loader algorithm you see on this picture. Algorithm of background process of service of control and activity of software modules. Dependence of malware attacks frequency on the executable file format are revealed. Fragment of the log file of documentation of events in the subsystem of control actuality of the client software of the information system of management of financial resource of HNU. The result of research and experience. The proposed technology to ensure the fault tolerance and survivability automated workstation of specialized information system based on the method of parametric control of software prevalence of client automated workstation provides a survivability high level of stability of the information system as a whole against malware. The result of research and experiments. The present method is implemented in the technology which implements the second local line of concentration to malicious software. The result of research and experiments. So, its implementation in existing system does not require significant cost as its function are combined with the existing service to support the relevance of software version of client workstation. Plans for future research. The direction of future research is to find ways to increase the efficiency of the proposed technology in ensuring fault tolerance and survivability of specialized information system. Thank you for your attention. Have you any question?
Thank you, Mykola. Dear colleagues, any questions?
Yeah, may I ask a question?
Yes, please.
So in your plans for the future work, you say that you would like to increase the efficiency of your technology. Yeah. So have you evaluated the efficiency, the effectiveness of your technology at the moment?
The proposed method of Parma increases the resistance to the information system of destructive effects of malware software.
So can you name some, I don't know, numbers, volumes and so on, according to your efficiency? In what way do you analyze the efficiency of your technology, of your system?
Рівень ефективності. Efficiency level.
I don't remember. I must see it.
Maybe it's your future plan, yeah, to conduct this
Yes.
experiment. Okay, thank you.
Okay, thank you.
Can I stop the presentation?
Yes, you may.
Thank
you,
you.
Mykola. So the next presenter will Volodymyr Mokrun. Is somebody here from?
Let's go to next presentation, maybe
Yes.
connection problem.
Some problem. Okay. Maybe Georgій Землянко, Володимир Торяник, and Vyacheslav Harchenko.
Yes, I am here.
Okay. Georgій, nice to meet you. Please.
Nice. Do you see presentation?
Yes. Start, please.
Okay. Yeah, okay. So good afternoon, dear participants. This report introduces a topic entitled IMSC-based assessment of Internet of Drone Systems, cybersecurity considering radio frequency vulnerability. So each topic was made by Vladimir Toryanik, Vyacheslav Harchenko, and PhD student Georgій Zemlyanko. So as you know now, the concept of Internet of Drones is gaining momentum. The Internet of Drones IoT provides a coordinated access to unmanned aerial vehicles that are referred as drones. So the ongoing miniaturization of sensors, actuators, and processors with ubiquitous wireless connectivity makes drones to be used in a wide range of applications, ranging from military to civilian. So in terms of network architecture, the Internet of Drones is similar to the Internet of Things. However, there are a number of specific problems or ideas that you can see on this slide. Consider the concept of IoT, which is about governance, strong authentication, wireless connectivity, and integration with third-party applications. You can see in this slide. So the most common vulnerabilities are shown on this slide. It's APT attacks, software-defined radio frequency, RFIF, and RFCV. So the vulnerabilities are demonstrated in more detail in this article. It's concept of radio frequency vulnerabilities and IMSA assessment of IoD. As in this slide, you can see the most common attacks on cyber systems. Cyber physical systems, sorry. The most relevant class of attack is unauthorized use of radio frequency. Vulnerabilities of the Internet of Drones are associated with the use of radio channel, to close most of them, such as mesh networks. The slide lists the Internet of drone subsystems for which APT attacks are possible. It's such navigation, authentication, identification, instruction detection, firewalling, and so on. In this slide, you can see the SDR system. So it's system which we used for penetration testing or monitoring for analysis our threats and vulnerabilities. So in this system, we can use the SDR system as IoT penetration testing for monitoring attacks of Internet of Drones. The possibility of using wireless technologies in IoT system are considered in this table. So you can use see the most popular wireless technologies such as Bluetooth, NFC, Wi-Fi, GPS, and so on. And the possibilities use these technologies in this Internet of Drones. In this scheme, we show the conception of system for model of interaction of drones or drone swarms with monitoring objects and control stations. In this slide, we shows the indicators that we were used in the construction of IMSC model. We show this in next slide. So the first, it's in this table. Its table shows the indicators that are the sources and targets of attacks on the properties of the Internet of Drones. And in the next table, we use this in the types of attacks and their effectivenesses, as well as to what losses they can lead. So in this also we use some criteria of type of effects for system. It's data loss, data destruction, control loss, and control substitution, sorry. So by this, we make the risk matrix, which shows the likelihood of attacks that were demonstrated in the previous tables. The parameters by which the control subsystem for wireless radio channel functions are presented in this slide. So we thinking about the function of such a monitoring subsystem can be the assessment of system physical audio parameters such as capicities of transponders, azimuths of radiation, gradients of power and azimuths, coordinates and speeds of transponders. And after this, when we use this criteria, the risk matrix is a little bit changed. So in this slide, you can see that that the influence of radio channel control subsystem on the likelihood of attacks is a little bit low. So as you can see, attacks 2 significantly reduce the probability of implementation, and while attack 3 dropped by 1 level, and the rest did not change. So in conclusion, the report demonstrated that main vulnerabilities of the radio channel using in SDR and also with Internet of Drones. So the use of the conception IMSC model for analyzing the implementation of attacks on the Internet Drones system was shown in some criteria for safety and security. And it proposed to use radio channel monitoring system to reduce the risks of attacks on the Internet of Drones. Further, the research is a method for construction cyber protected wireless system with the technology wireless 2.0 architecture, intelligent self-control as cognitive radio and intelligent radio signal processing. Thank you for attention.
Thank you, Georgi. It was very interesting. Colleagues, any questions, please?
May I ask you?
Yes, Thomas, please.
Could you tell us whether you focused on centralized controlled IOD or IOD with distributed control or both?
Centralizing.
Okay, and could you imagine the application of your approach to distributed control like swarms?
we're not thinking about this now about applications. We only make a criteria and IMCA model. In the future, we planning to look at applications and how it correctly uses by this system.
Okay, thank you.
Thank you. Colleagues, no more questions? Okay, thank you. Harry, please close your presentation, please. Let's move on. Greetings to Odessa. Alexander Drost is the next speaker, please. Are you ready?
Yes, I am ready. And I show my screen. My screen is seen.
Yes, it's visible. Okay, thank you.
Thank you. Odessa National Polytechnic University team presents a paper titled Checkability Important for Fail Safety of FPGA-based components in critical systems. You can see contents, and the first question is associated with relevance of the problem. High-risk facilities in energy and transport are becoming a natural environment for humans. They permanently increase the quantity, complexity, and power. In order to limit risks, it is necessary to develop information technologies implemented into safety-related systems. These systems are aimed at ensuring functional safety of both the system and the control object for preventing accidents and reducing the consequences. Functional safety is based on the use of fault-tolerant solutions for which multiple failures are the biggest challenge. Fault-tolerant system can be safe only if it is checkable. A lack of checkability doesn't allow the fault-tolerant circuit to be transformed into a fail-safe one. Study of checkability for the fault-tolerant solutions, including FPGA circuit, becomes an urgent problem. State of the art. We took into account fault-tolerant solutions which are designed to possess one or two faults and cannot withstand multiple failures. Source of multiple failures, including common cause failures, cyber attacks, hidden faults. International safety-related standards, which pay significant attention to common cause failures, show common cause in coping erroneous solutions and propose to use multi-version technologies with development of different kinds of diversity. We took into account also a problem of hidden faults, which can accumulate during normal mode and reduce the fault tolerance of circuit in emergency mode. This problem is known from failed attempts to detect hidden faults by using imitation modes, which are very dangerous, and which aimed at recreating emergency conditions and repeatedly resulted in them due unauthorized activation by human or failure. The planned activation of such modes executed with the shutdown of emergency protections has become one of the causes of the Chernobyl disaster. Checkability, with its evolution from testability to dual mode checkability in safety-related systems, a lack of this checkability results in multiple failures associated with a hidden fault problem and resist the conversion of fault-tolerant circuits to fail-safe. FPGA components of safety-related systems were a problem of insufficient checkability is shown in load memory. The presentation is aimed at assessing the checkability of digital circuits in that part of it which is important for ensuring fail safety in fault-tolerant FPGA components of safety-related systems. The main source of the suggested method is associated with a resource-based approach, which explores the integration of the artificial world created by human into the nature one. Define 3 levels in the development of models, methods, and means: replication, diversification, and self-sufficiency as a development goal. The resource-based approach identifies a safety-related system as development of computer systems with diversification of an operating mode by its division into a normal mode and emergency one. A problem of multiply failures, including hidden faults, which make the fail safety of fault-tolerant circuit dependent on their checkability. The hidden fault problem is a growth challenge when a safety-related system rises to a level of diversification in checkability that becomes different in normal and emergency mode for matrix circuit. But system components continue to be stamped at a lower level of replication using matrix structures, including FPGA design. Diversification of checkability in critical areas, highlighting the part of it that is important to safety. Main provisions of the method. This method evaluates the checkability of a digital circuit with load-oriented architecture in the part that supports the fail safety of fault-tolerant FPGA components in safety-related system. The checkability of a digital circuit with load-oriented architecture should be assessed in terms of controllability and observability. The controllability of the load memory is provided in its addressable bits. The observability of the memory load bits is manifested in its use for generating a result when bit corruption determines an erroneous result. The observability of the memory load bits in emergency mode classifies them among the many important for ensuring the functional safety of the FPGA component. The fail safety of fault-tolerant circuit is provided in the memory load bits, which are observable in both normal and emergency mode. The proposed method defines 2 sets of memory load bits, which are important for fail safety of fault-tolerant FPGA components. These sets consist of bits that support and, on the contrary, violate fail safety of fault-tolerant components respectively. The method performs the following steps: simulation of the FPGA component determines the sets of memory load bits addressed in the normal and emergency mode respectively. Obtaining the sets of bits which are controllable in both modes and only in the emergency mode respectively. Simulation of the FPGA component for the sets determines memory load bits which are observable in normal and emergency mode inputs respectively. Obtaining the set of bits important to the safety of the FPGA components and the sets of checkable and dangerous bits which provide and violate the fail safety of fault-tolerant circuit respectively. Evaluating the checkability and its lack, which determine the degree of fail safety or its deficiency of the fault-tolerant circuit. Experimental verification of the method was carried out using Quartus Prime card on the example of a study of a 4-bit iterative array multiplier implemented in Intel chip. The circuit simulation was carried out using the program implementation of the method. The program was developed in the free Delphi demo version. The value of the factors smaller than the threshold referred to the normal mode and the rest emergency one. As the threshold increases from 8 to 64, checkability increases from 62 to 91%, and its deficiency decreases from 38 to 9%. Conclusions. Safety-related systems ensure their own functional safety and the safety of control objects using fault-tolerant solutions, for which multiply failures are the most dangerous. One of the sources of multiply failures is associated with the problem of hidden faults, which can be accumulated during a normal mode and reduce the fault tolerance of circuits with the onset of emergency mode. This issue demonstrates the importance of checkability in transforming fault-tolerant solutions into fail-safe ones. FPGA component designed, widely used for critical applications, inherits the problem of hidden faults in memory of the load units. The proposed method defines a set of memory load bits that are important for fail safety of fault-tolerant circuits. These bits are split into two sets, which provide and, on contrary, violate the fail safety of the circuit. Bits of the first set are observable in both normal and emergency modes. The second set contains memory load bits that are observable only in emergency mode and constitute a deficiency of checkability required to transform a fault-tolerant circuit into a fail-safe circuit. Thank you very much for attention.
Thank you, Alexander. Colleagues, do you have any questions?
It's a very important problem associated with fault-tolerant circuits, which can be fail-safe only if enough level of checkability. It's my presentation devoted to these problems.
Alexander, I have a question. Did you use some what type of FPGA did you use in order to evaluate some experiments?
We designed arithmetical units, for example, multipliers, iterative multipliers, dividers, and load-oriented architecture of these decisions. We simulate with use of program developed as a free demo version of Delphi.
I see. So you didn't use such as Altera, Cyclone, no, just a software evaluation, yes?
Yes. Yes.
I see. Thank you.
Thank you.
Colleagues, any more questions? No, thank you. Alexander, thank you.
Thank you.
Okay. So the next presenter is Alexander Martinyuk. Are you here? Or maybe Ludmila Sugak, Anna Stepova,
Yes.
Viktor Antoniuk, and Igor Mileyko.
Good morning, dear colleagues. I show my presentation now. May I show it? May I show, demonstrate my screen? I can't include my demonstration now, or demonstration. Oh, yes. Okay.
Do not hear you. Alexander, please. Please unmute yourself.
Oh, okay. You listen me now.
Yes.
Oh,
You may
it's
press F5 maybe.
excuse me.
May you press F5?
F5, yes.
Oh,
Okay.
for full screen.
F5, F5. Okay.
No. So
Mm. But F5 don't work.
okay, so you may show in such a way presentation.
And the purpose of work is to increase the completeness of behavioral testing of the function of this distributed information system through additional analysis of energy consumption. Main task is being solid development of a model for analyzing energy costs based on extended battery net with features of states and structures of localized and moving energy variables and tokens. The model allows you to determine the conditions for the use of energy costs in behavioral testing of these. In this picture, we see the example of testing subsystem into this distributed information system. Red color are components, are the test components. Emphasis in this testing of the functioning of this can be made on the characteristics of energy consumption. In first, instantaneous energy structures states for this component and various composition of these components, which are essential for analyzing the system performance. In second, dynamic energy structures traces for these components interacting in these operations procedures. And third, characteristics energy structures traces of the second type, which make it possible to identify the reference behavior of these components by their energy consumption. This picture demonstrates a hierarchical extended battery net with energy consumption. For the battery net, diagrams of instantaneous energy states with marking and events and actions have the next form. Energy states give the values of this energy consumption and the dependencies for the battery nets. Switching values for events and action of energy state characterize instantaneous local energy consumption. Energy state diagrams perform the selective analysis of energy consumption of these in some critical states for battery net or its subnets. Representation in time of energy consumption values for energy states gives sequence diagram of the next form. This picture demonstrates the checked properties of extended battery nets and this cascade. Energy tokens counters determine dynamic structures from energy states during the functioning of these. The analysis of dynamic marking and accumulation of energy consumption values in tokens counters is carried out when modeling battery nets with comparison with reference value. Three-level hierarchies of possible energy input token are formed for, in first, component battery subnet, in second, energy structures, and third, positions and transitions. For the initial token leaf of position in initial state for PetriNet, leaf 0 is executed. For the node token node of the topological structure, the accumulation of value of the lowest token in hierarchy is in effect of sum 5. Sequence diagram are format next sums when unfolding for point in time the values of energy consumption for energy structures. Energy costs are determined during the execution of topological energy structures. The expectation readiness execution in accordance with mandated functions of tokens are possible. For example, node with and PetriNet, the next inclusions are valid. The energy structures are the part of the fragment of functioning of PetriNet and are the part of common identifiers in the alphabets of events and actions. Special energy structures, energy identifiers, are in alphabet of energy consumption values for events, actions, tokens, counters. Energy alphabets are extended with multiple energy inputs. Expansion of energy alphabet allows to define words for combinations of energy costs of events and actions. Complex energy structures and identifiers have next forms and approaches. The first particular approach to the definition of construction of energy identifiers is based on mirroring of common identifiers of position transition of PetriNet. Energy identifiers are defined by mapping for common identifiers as to position transition and their characteristic behavior. Mapping M has the next form N. Energy identifiers assume for each identifier the injectivity property that is its next form. Each energy identifier is unequally incident to its corresponding position and transition. In the second approach, energy identifiers are determined out of relation to common identifiers on the basis of their definition of the energy characteristics, Bohr code of certain position or transition. Despite Reagan-Scott energy automata, energy identifiers have the next form. It's also more expanded to use energy identifiers in the testing of functioning of this in connection with input-output identifiers as the essential addition of in terms of the efficiency of analysis. This picture demonstrates the modified Rabin-Scott automata for energy identifiers. The analysis uses the diagram of local energy states and dynamic behavioral energy topological structures, as well as sequence diagram based on them. For the analysis of this, including the energy one, the main 7th step of the preprocessor and initial stage for PetriNet are possible. This input, output, and energy testing stage include the 7 steps too. Estimations for steps of procedures present for the next part. PetriNet, maximum length of search, automata Rabin Scott, and the total estimate of the fields does not exceed then this expression. The estimates present the upper limits for applicability of the abstract model, and the reduction is expedient due to the decomposition of battery net. This picture demonstrates the temperature monitoring of component of this into diagrams of time states with 2.5.2 broker and server in Internet of Things system. This picture demonstrates the basic algorithm of energy check. And this picture demonstrates the normalized model for database for energy check into subsystem. This work proposed the development of the model battery net in the behavioral testing of this, supplemented by the analysis of energy consumption. This in turn allows you to determine the steps of the behavioral testing procedures for this, extended by special testing the energy consumption, and increases the completeness of the common behavioral testing of this. Thank you for attention, and I'm ready to answer your question, please.
Thank you, Alexander. Colleagues, do you have any question?
Yeah, I've got one question.
Yes, please, Svetlana.
So thank you for a really interesting presentation. And my question is, what is the novelty of your research? Maybe your model gives more efficiency, or maybe something else. So what is the novelty of your research? The main advantage?
No, we now use our subsystem for system of Internet of Things, for smart home, for temperature subsystem in smart home, and lighting of smart home system. This system is in Internet of Things all, but any other system as web services, web grid, web cloud systems, and their subsystem may use this approach to verification of functioning, because these models and method based on it used the behavioral approach to verification, or approach on system on structural functional level, high level. These details of realization is not important. It's not important.
Yes, thank you for your answer.
Okay, thank you. Any more questions? No, thank you. Thank you, Alexander.
Thank you very much.
Okay. Greetings to Lviv. Victor Melnik, are you here? Are you ready?
Good morning. Can you hear me?
Yes.
Yes, okay. So I will start my presentation, just a moment. I will share my screen. Okay, so again, my name is Victor Melnik. I'm representing two organizations here. First one is Lviv Polytechnic National University, and the second one is Catholic University of Lublin, the John Paul II Catholic University. And my report I want to present today is entitled Data Structures and Lookup Algorithms Investigation for IEEE 802.15.4 Security Procedures Implementation. The plan for this report is following: the motivation, state of the art, objective, efficiency criteria. We will overview these procedures, estimate the characteristics, and we present some data structures and algorithms that we have analyzed. Afterwards, we conclude with these data structures and provide some summary of that. The first is motivation. As you can see here, there is a IEEE, which standard which defines MAC and physical layers of the wireless personal area networks protocol stack. Security services are provided on MAC layer and on application layer. For MAC layer, the security services are defined in the standard IEEE 802.15.4. The execution of the security procedures usually splits between the programmable microprocessor or microcontroller and a specialized processor. The last is used to execute most intensive security-related computations like AES, CCM, star encryption and authentication, and the first normally performs some not intensive but quite time-consuming security checks, which are executed in the form of lookup procedures, which we examine in this report. Since wireless personal area networks devices are resource constrained normally, it is extremely important that security checks have to be performed in a short time, provide compactness, low power consumption. This is very important. Here we can see on the slide the general structure of the MAC security subsystem. It contains security processing support unit, as we can see. And this unit executes data fetch and analyzes these lookup procedures while the security data are retained in a MAC layer PID, so it's a PAN information base. Depending on the approach used, lookup procedures may be implemented in hardware, as we can see here, or in software. The first is, for example, in specialized processor. The second one is in a programmable microprocessor or microcontroller. The research which is presented has been carried out as a part of the project executed on development of the security subsystem for VPN, wireless personal area networks. And the objective of the research is the study of effective implementation of data retrieval operations in the standard security procedures, which is quite important, but not enough covered in the existing literature. There are following efficiency criteria defined for lookup solutions: speed or time complexity, memory needs, scalability, and hardware implementation feasibility. Encryption keys and related information are stored in so-called MAC key table in the PAN information base. They are organized as a specific data structure, which is called key descriptor. There are 4 security lookup procedures that need to be implemented in the system on chip, which implement the standard. This is key descriptor lookup procedure, blacklist check-in procedure, incoming key usage, policy check-in, and incoming key security level check-in. The first one compares the pair of input values, key lookup data, and key lookup size with contained into the key descriptor pairs of values, and thus checks that communicating part of devices use exactly this key descriptor. The blacklist check-in procedure determines whether the send and remote device belongs to the devices that use identified key. The incoming key usage policy check-in procedure determines whether identified key may be used to unsecure the frame of present type. And the last one checks whether the frame to be unsecured corresponds to the minimum security requirements that are applied to this type of frame. The first task to solve, while we need to select the appropriate lookup algorithm and data structure, is analyzing the security data characteristics, namely the type and size of data used as a key for the lookups and the number of keys involved in the lookups at the same time. These characteristics were analyzed for each mentioned lookup procedure. Here we can see the key descriptor lookup process, and here is a pseudocode for this procedure implementation. We can see here a number of key descriptor entries. Each contains a key and related information. The search should be performed in parallel, so this is ideal case in this descriptor entries, if it is, of course, possible. On the following slide, we can find a description of the fields and estimated sizes and types of the record. And also, we found elements that could be served as key for lookups. Thus are, here we can find the lookup size, for example, and lookup data. Other lookups within key descriptor are organized similarly, and here we can see device descriptor and key descriptor lookup processes within the blacklist checking procedure. And also here we can find a pseudocode for this procedure implementation. Description of the fields and estimated sizes of device descriptor report is given in the table. And also here the elements are highlighted that may be used as keys for the lookups. On this slides, we can find a key usage descriptor lookup process in incoming key usage policy checking procedure and the pseudocode for this procedure implementation and a table beneath this description of the fields and estimated sizes of key usage descriptor record. The last one, the last procedure lookups within incoming security level checking procedure is performed in another table, in next security level table that stores security related information. And this process of the lookup is given here in the figure, and a pseudocode is here also provided. The description of fields and estimated sizes for this security level descriptor record given in the table. Here we can find also the elements that may serve as keys for lookups. As a result, we can state that the keys are all bit strings, and the longest is an extended device address of 64 bits. The amount of memory used to store one encryption key or key descriptor record is, we can see 418 bits or 52.25 bytes. So this is for the case if key ID lookup list and key device list and key usage list is in there have only one entry each, so it's very optimistic case. The three data structures, trees, tries, and hash tables we have considered for security data indexing. For each of them, we present the algorithms for performing operations that can be used to insert or delete a node into or from the data structure and to find a desired node in it. In the following slide, the first data structure, the binary search tree structure, is represented. Here we can see an example of some binary search tree that contains ordered list of numbers. And beneath the pseudocodes for insert and lookup and delete functions that can be used with BSTs are given. Tries is another tree-shaped data structure that has been analyzed. An example of some binary digital search try is shown here in a figure. And the basic try structure has several shortcomings which can cause performance loss in information retrieval system. For example, when nodes of the try have one single child only and try becomes very deep. There are some optimization techniques on tries that can be used to improve their characteristics, which are follows: compact bit string tree and Patricia tries, compact Patricia or CPET tries, hierarchical CPET tries that can be used to improve their characteristics. Also, the pseudocodes for insert, we can find lookup and the delete functions that can be used with compact Patricia tries. They are given here on the slides. If we compare tries with trees, we can conclude that lookups are faster on trie structure than on BST since the lookup complexity is lower. Comparison operations are cheaper in tries. Also, tries have lower memory needs as well since they share prefixes. There are also several contrasts that we need to mention. The HCPET tries provide better characteristics on the memory needs and performance as compared to other trie types, but the computational complexity is much higher. Also, lookups have strong sequential key retrieval property on tries, and our keys will be retrieved one by one. That is not suitable for ZigBee or other IEEE 802.15.4 based systems on chip. The third data structure we analyzed is a hash table. It is represented in given slide. Hash tables provide a very fast way for looking up data as a long key is fed into the hash function. The corresponding short hash table index is obtained and the search record or pointer on its location in the memory is instantaneously found. On the right top corner here, we can see two schemes for hash functions operation. Beneath there are pseudocodes for insert, lookup, and delete functions for hash tables, and also there are pseudocodes for two auxiliary functions, namely resolve insert collision and resolve lookup collision. Such collisions may happen as identical short hashes may sometimes be obtained from different long keys. We have summarized data structures efficiency for lookup procedures execution based on criteria enumerated on the beginning. Hash tables based algorithms promise the highest speed. With hash tables, any node can be looked up, inserted or deleted by simply calculating the value of hash function. This complexity is lowest comparing to others, and it doesn't depend on the number of keys, but it can degrade if collision happens. Memory requirements of hash tables are reduced as well comparing to other structures. Regarding the scalability, trie-based solutions are expected to provide higher scalability than tree-based ones for two reasons. First, tries operate on bits and not bit strings as trees do. Second, in tries, common prefixes are represented only once, while in trees, they are repeated each time they occur. Since in the case of hash tables, time complexity doesn't depend on number of keys, the scalability of hash tables is considered the highest among the data structures presented. Hash tables are favored also for a hardware implementation point of view because algorithms are enough simple and the main operation that has to be performed is computing of hash function values. Tree-based algorithms are also simple. However, they require fast handling of bit strings representing keys, and it may somewhat slow lookup times. Finally, despite the fact that tries operate on bits instead of bit strings, we consider them the most inappropriate for hardware implementation among the presented approaches, since the algorithms that operate on them are quite complicated for resource-limited embedded devices. Conclusions are drawn here. You can find it. We suggest the most important. We suggest that the hash tables based approach is best to be implemented, and the tree and trie-based approaches should be considered for implementation only if execution time and resource permit. Thank you for attention. Please, if you have any questions, you can ask.
Yeah, thank you, Victor. Colleagues, any questions? Okay, so Victor, I have a question. Thank you for a very interesting presentation. As I saw, you evaluated computational complexity of your solution, yes. And I have a question. Did you prove it trying to realize it in some language programming, using some language programming to prove it, this complexity?
No. We don't use any experiments here, but we used some empirical, I would say, more empirical results. Our approach was calculated time and complexity in the terms of number of operations. That's all.
I see. Thank you.
May I ask a question?
Yes, Lana.
Yeah. A similar question according to this slide. So here you evaluate efficiency according to scalability and hardware implementation using such terms like medium, good, not good, and so on. So what were the criteria to state that it is medium, good, or not good?
Okay. Sometimes it's quite hard to compare, for example, two structures, BST and trees or trials. For example, trees with trials. So we don't perform some strict comparisons. That's why we use such light approach, like medium, good, or not good. So we are based on the following, that not good, it means that we have a higher complexity of the algorithm. And for resource constrained device, so this is not some absolute estimation, yes? We estimated according to the requirements of this application. If we are talking about the resource constrained device, that the energy is one of the most important resources, we need to say that hardware implementation of trials, which are very compact, which may be very fast, are not good for this, exactly for this application. Also, we have to say, for example, if since in trial we have only one possibility to check the lookup keys one by one, this is also not suitable for this implementation, because we would like to perform these checks in parallel. This is why we say that this implementation is not sufficient for this. Others, for example, hash tables, they provide possibility to perform it in parallel, and only one operation is calculation or computing the hash values need to be performed. This is okay, this is how it looks like.
I see. So as I understand, you as developers were the experts who evaluate in such way your system, not customers, yeah, but...
No. It was a research project on development of such a subsystem. I was developing this subsystem as a leading as a manager, as a responsible developer, and this was some part of that project. You can find some other, I think, a lot of information in my previous papers that I have already published on this topic. So about the security implementation, about the subsystem for this low power personal area networks, etc.
Okay, thank you. I will study. Thank you.
Okay, thank you, Victor. Thank you, Victor. Okay, the next presenter is Kira Bobrovnikova from Khmelnytskyi National University. Please, are you ready?
I'm ready. Yes. Can you see my presentation?
Yes.
Dear colleagues, I am Associated Professor of Computer Engineering and System Programming Department of Khmelnytsky National University, Kira Bobrovnikova, and I am pleased to present a topic technique for IoT cyber attack detection based on the energy consumption analysis. The Internet of Things and smart home conception have become an important part of modern society. On the other hand, the growing number of IoT devices, which are often released without any security features, makes them a desirable target for cyber criminals. Since the limited battery capacity of smartphones does not allow them to be used for profit, that smart TVs, set-top boxes, and other devices are popular with cyber criminals. In the regard, cyber criminals create a new malware for test device. As we can see, new families of IoT malware are being detected recently. Unprotected IoT devices join the ranks of botnets that are most often used to launch DOS attacks or as VPN exit nodes. Crypto mining is another popular way to monetize compromised IoT devices. The availability and insecurity of IoT devices has led to a rapid increase in the number of IoT cyber attacks in recent years. Despite the larger number of different developed methods for detecting and preventing IoT cyber attacks and malware, IoT devices is still incredibly vulnerable and suffered a wide range of cyber attacks and their financial and public relation consequences. Therefore, there is a need to develop a new approach for the IoT malware and IoT cyber attack detection. IoT devices energy consumption monitoring is a possible way to detect to the performing attacks which require significant energy consumption, for example, DOS and crypto mining. In addition, energy consumption analysis-based approach is more secure in cases the kernel of the device is already compromised. So far as once the device is compromised, the data integrity cannot be guaranteed. The proposed technique for IoT cyber attack detection uses analysis of the device's energy consumption footprints and also applies analysis of the IoT software sequences of codes to improve the accuracy of IoT attack detection and localize the IoT malware onto the IoT devices. To effectively build IoT devices' energy consumption footprints, it is necessary to take into account the different energy consumption-related user preference modes for such systems as heating, ventilation, air conditioning, lighting, and functioning of different IoT devices. Also, let's define the energy consumption control function F, which keep up the energy consumption of the IoT device according to a given user preference mode. The proposed technique consists of two stages, learning and detection stage. Internal learning stage includes the energy consumption analysis and the opcode sequences analysis. At the learning stage, the energy consumption of each IoT device in the IoT network for different IoT user preference modes in the absence of IoT cyber attacks, also in the presence of IoT cyber attacks is measured at a certain interval and at equal sub-intervals of time. Based on these measurements, the set of IoT devices' energy consumption footprint are constructed, part of them labeled as normal footprints and entered into the labeled data matrix, rest of them entered on the unlabeled data matrix. After that, the semi-supervised learning of the fuzzy Siemens classifier by using the labeled data matrix of energy consumption footprints are performed. But IoT devices' total energy consumption monitoring cannot provide an answer to the question of localizing malware as a source of IoT cyber attack. Therefore, the proposed technique for IoT cyber attack detection uses analysis of the IoT device's energy consumption footprints and also applies analysis of the IoT software code sequences to improve the accuracy of IoT attacks detections and localize the IoT malware on the IoT devices. The steps of the learning stage of code sequences analysis are presented on the slide. With the IoT devices of code sequences analysis at the learning stage, the assembly representation from the benign and malicious IoT binary executable examples are extracted. From this assembly representation, maximal sequential pattern of codes are extracted by applying of sequential pattern mining algorithm. For each maximal sequential patterns of codes, the inverse document frequency value IDF, which reduces the weight of commonly used maximal sequential patterns of codes, is calculated. To determine the order of maximal sequential patterns of codes in the feature vectors, they are sorted ascending values of inverse document frequency. To assess the relevance of maximal sequential patterns of codes for each such pattern, weighted term frequency are calculated as following. Weighted term frequency is the result of whitening the term frequency TF with the relevance of each opcode and are computed as the product of sequence frequency and the calculated weight of every opcode or in the maximal sequential patterns. Term frequency assesses the importance of maximal sequential patterns within an IoT software executable. Weight of every opcode is based on the calculation of mutual information, which is a measure of statistical dependence of 12 variables. In this case, there are the single opcode or and whether or not the software was malware. From obtained for each maximal sequence patterns VTF value for each IoT software feature vectors of its relevance is built. In the process, the vector whose length is greater than the median length of the all obtained vectors are truncated. Vectors whose length is less than the length are padded with zeros. The part of constructed vectors labeled respectively as benign or malicious and entered into the labeled data matrix, the rest of them entered on the unlabeled data matrix. On the detection stage of the proposed technique, the energy consumption of IoT devices is measured and analyzed. In the IoT devices has an abnormally high energy consumption. This may indicate that it has carried out cyber attacks. With aim to identifying the suspicious programs and its localization, software code sequences analysis was performed. With this aim of codes, maximal sequential patterns mining in the assembly representation of suspicious binary executable is performed. For obtaining maximal sequential pattern, their relevance calculate and feature vectors for the suspicious software is built and analyzed. With aim to detect IoT cyber attacks, in proposed approach, the semi-supervised fuzzy C-means classifier was applied. As clustering object are the IoT device's energy consumption footprints, but instead of the Euclidean distance, which is used in the basic C-means algorithm, for IoT devices energy consumption footprints, clustering as a distance measure, the dynamic time warping DTV was applied. The result of clustering is a fuzzy partition matrix where each element of the matrix determines the degree of belonging of the certain element of the set of clustering objects to the certain clusters. Thus, each clustering object with a certain degree of affiliation belongs to each of the clusters, each of which denotes normal energy consumption in a specific user model or increased power consumption indicate an attack. For the feature vectors of OPCODES relevance calculation, instead of the Euclidean distance, the Mahalanobis distance was used. In this case, each feature vector with a certain degree of affiliation belongs to each of the cluster, each of which denotes benign software or certain type of malware. Let's take lambda as the threshold values of clustering object belonging to the cluster at which the clustering object is considered as malicious. In order to assess the effectiveness of the proposed approach, a number of experiments were carried out. The ARM platform was chosen as the target IoT platform for the experiment since it is one of the most common IoT platforms. Such variety of ARM-based IoT devices have been used. Each energy consumption footprint was obtained by taking measurements after 0.5 seconds within 3 minutes when the IoT device is performing an attack and normal operation. Also, using the proposed approach, sequences of opcodes were extracted and analyzed from malicious software samples that carried out Tether attack. Tether software samples were disassembled by using the IDA Pro to obtain its opcodes. For opcode sequences, mining hash-based partition seconded pattern mining algorithm was used. Some of the data, about 10%, were used for training. The rest of the data were used as testing data to access the effectiveness of the proposed approach. In order to assess the effectiveness of the proposed approach, the following metrics were applied: accuracy and F-score. For the purpose of classifying the malicious samples, separate vector matching, nearest neighbor, decision tree, random forest, and semi-supervised fuzzy Siemens classifier were applied. The result of the experiments showed high efficiency of IoT cyber attack detection based on the energy consumption analysis. At the same time, is it showed from the table 2, the analysis of the opcode sequences of suspicious software will allow localizing the program on the device, which is the source of the IoT cyber attack. As can be seen from the experimental results, the highest efficiency was obtained using semi-supervised fuzzy Siemens clustering. Thus, taking into account that high energy consumption may indicate that the IoT device is carrying out cyber attacks, which require increased energy consumption, a new technique for IoT attack detection based on the IoT device's energy consumption analysis was proposed. This technique takes into account the energy consumption related users' preference models. Therefore, with AIM cyber attack detection, the energy consumption of IoT devices is matched and analyzed. For the purpose of localizing the software on the device that performs the cyber attacks, test software opcodes analysis was performed. The experimental results show that the proposed approach allows detecting the performing by the IoT device such attacks as, for example, DOS, reach high efficiency at a level of about 99.88 and localizing malicious software to the devices with accuracy of about 99.66. Thank you for your attention.
Thank you, Kira. Colleagues, do you have any questions?
Professor Kira, may I ask a question? how did you measure the energy consumption, and how do you simulate the attack?
For with aim attack simulation, malware software was downloaded onto the devices, and the attack were simulated in a closed network.
Mhm.
The energy consumption was measured sorry, my English.
Oh, it's okay. I'm also not perfect.
In time length of 3 minutes, I'm sorry. I'm sorry, my English.
Okay, maybe we can discuss it later. Thank you very much.
I'm sorry.
Okay, it's okay. Thank you.
Any more questions, colleagues? No? Thank you. So the next presenter is, I suppose, colleagues from Odessa. It's Konstantin Shcholkin, Alexander Drozd, Olena Ivanova, Ruslan Shaporin, and Mykola Kuznetsov. Who is ready?
Yes, I am ready. Good morning, dear colleagues. Excuse me, I lost my voice a little bit, so my presentation will be a little bit loud. Okay. Can you see my screen?
Yes, we can. Okay, everything is okay.
Dear colleagues, my name is Konstantin Shcholkin. I am associated professor of Odessa National Polytechnic University. Topic of my presentation, an approach to Stega container organization in FPGA system for approximate data processing. In this work, we consider the problem of embedding the digital watermark into program code of FPGA chips in steganographic way. Digital watermark will give the possibility to place the extra information hidden from an outside observer in the program code FPGA. This can provide for example, integrity monitoring of FPGA program code process. Main principles of digital watermarks. The fact of digital watermark presence in program code is hidden. Digital watermark does not change program code size and operation of device. And digital watermark can be read from the program code if someone has a Stega key. The set of access rules to elements of digital watermark. The steganographic approach to data protection is based on imperceptible embedding of protection data in the information object, Stega container. The main conditions for such embedding are immutability, of the main functionality of Stega container as a result of embedding and indissolubility of embedding data from the Stega container data. The following assignments of steganographic methods of the types of Stega container has developed. For multimedia Stega containers, methods for non-equivalent change in the data of elementary container units. The base of steganography method in this direction is that multimedia data are analogous and approximate natural. For containers with exactly represented data, for example, program code, for example, FPGA program code, use methods for equivalent transformation of container data. Unlike multimedia Stega container, the program code is not approximate data, but exact. We consider that the structure of FPGA program code has the potential to perform not equivalent embedding, similar that we use for multimedia Stega container as well. Such embedding is possible for FPGA program code implementing arithmetic operations on approximate data. So the goal of this work to estimate the volume of the Stega container obtained by applying non-equivalent transformation to the FPGA program code. When performing arithmetic operations, require result are the same size of operands. When performing operands on n bit result must be obtained. For a number of arithmetic operations, the size of the result naturally exceeds the size of operands. In this case, the full result is calculated first. After that, rounding the performed and the lower bits is removed. Let A and B is operands with n bits, from 0 to n minus 1. And C is result of arithmetical operations with 2n bits from 0 to 2n minus 1 bits. To convert the result C to the required format, the high-ordered n bits of result are retained and the low-ordered bits are discarded. This bit of complete result form two-order set. Most significant bits and least significant bits, discarded bits. The main elementary units of FPGA structure are wood. These are generators of logical function of m variables, where m is number of inputs of the wood units. Such chip contain wood units that are used to calculate the least significant bits, and the operation result and do not have any effect on the most significant bits. L is set of all woods in FPGA project, and LIE subset of essential woods, woods that are involved in the calculating of least significant bits only, and not involved in the calculating of most significant bits. The program code of essential wood, essential wood of this kind. The program codes of essential wood can be non-equivalently modified in order to stenographically embed additional data into it. This modification will distort the result, but only in the last significant bits. Since these bits are discarded during rounding, the modification of this program code of LIE will not affect the final result converted in the used format of the number of operand bits. It's necessary to evaluate what volume of Stega container provides the proposed not equivalent approach to data embedding. For this purpose, an experimental evaluation is performed in which a Stega container are binary multipliers of different size implemented on FPGA. The initial data for experiments we formed using the CAD system Intel Quartus Prime and the software that we developed. 5 FPGA projects we created in the Intel Quartus Prime. Each of these projects implements a multiplier of corresponding size. For the experiment, we used iterative array multipliers with operands of 4, 6, 8, 11, and 16 bits. For each of possible values of operands and AB, the following steps are performed. We calculated 2n-bit result. The correct values are fixed at the output of each the FPGA project wood units. The values of the output of each FPGA project wood are inverted sequentially, changed from correct to incorrect value. For each of this distortion value, the result arrows is recorded. Each of the wood units in project is associated with the maximum value of error that arises as a result of a distortion of the output value of this unit. In this slide, you can see main windows of software which we developed for this experiment performed. These windows shown for 8-bit multiplier with 101 wood units. This you can see number of wood units and minimum and maximum errors as a result of this distortion. And bottom of this windows, we can see statistics of experiment results. In this slide, you can see experiment results. Column of this table is size of operands and final results. Next, size of results before rounding, number of wood units in project, and number in essential woods in the project. You can see that portion of in essential wood in this all this project about 40%. And in this rows of this table, you can see evaluate of minimum and maximum volume of Stega container. The result of experiment made it possible to obtain the number of essential wood in multiplier circuit implemented on FPGA. Since of the value of the output in essential unit do not affect of most significant bit of the results program code of these units can be subjected to non-equivalent modification. Thus, the number of an essential unit make it possible to estimate the value of Stega container format in environment of the wood circuit of the multiplier. We propose approach that allows steganographic embedding of additional data into the program FPGA program code. In contrast to the known approach, it's proposed to do this not by means of equivalent changes but by means of non-equivalent modification of the FPGA program code. To implement this approach, the proposed to identify essential woods units in the structure of FPGA system, which perform the processing of approximate data. In this case, a hybrid scheme of steganographic data embedding in FPGA program code appears. This scheme both embedding approach, equivalent and non-equivalent, can play the same of different roles. Hiding monitoring data, obfuscating of program code, and false embedding. For example, one approach performs embedding to hide monitoring data, while the other of this to code obfuscation or for false embedding. Thank you for your attention. This is the end of my presentation.
Thank you, Konstantin. Colleagues, any questions? No. So I have one. Konstantin, did you evaluate the computational complexity of your solution?
Okay. Complexity of solution in these rows of this in these rows of table, you can see a number of wood units in circuit. Approach which we propose not modificate complexity of this project, not decrease and not increase this complexity. So
it's no matter how much LUTs did you use, yes?
Yes, yes.
Okay, thank you.
May I ask a question?
Yes, Ivana, please.
I want to ask how we can see, or anybody can see that watermark is in that code.
I didn't recognize your.
Yes, recognize
well.
your watermark presented.
Could you repeat, please, you ask?
Як ми можемо, можна я по-українськи скажу, як ми можемо розпізнати, що знак є присутній, цей водяний знак є присутній, чи ми, чи хтось, чи ніхто не може ніколи розпізнати? Як знати, що цей знак там є присутній?
For extract digital watermark from this Stega container, we need to have Stega key. Stega key is special data for special data is located this information in Stega container. So another observer not recognizes this data in Stega container, but person who has Stega key, this information can be extracted.
Thank you.
Thank you, Konstantin, colleagues. So the next speaker is Antonina Kastalyan, please.
Thank you, Sergey. One moment, I'm sharing my screen. I hope you see my screen.
Yes, everything is okay.
Great. Good morning, colleagues. I'm Antonina Kastalyan, and I want to present our works, K-means clustering of HoneyNet data with unsupervised representation learning. As you know, malicious actions on the computer network threaten the stability of its operation and security of information. Intrusion detection systems must be able to detect various types of attacks, including those attacks about which no prior information exists. The approaches to detect network attacks can be divided into three base groups: signature-based methods, supervised learning methods, and unsupervised learning methods. Each of the approaches has advantages, but also disadvantages. For example, signature-based methods are unsuitable for new types of attacks. Supervised learning methods require labeled data sets. Unsupervised learning methods handle large unlabeled data arrays with mixed normal and malicious traffic. The analysis of it may be a challenge. Honeypots and honeynets are used to collect only malicious traffic. The advantages of honeypot's use are maintaining independence from the working environment, identifying zero-day vulnerabilities, reducing the false positive rate, and collecting data on malicious acts. So the objective is to identify patterns of attacks, including new ones, on the basis of data collected by a honeynet. Identifying patterns does not provide an unambiguous procedure for any types of data. Different clustering methods provide different group separation. Even the same clustering method can lead to different results with different initialization. This is one of the reasons to use different approaches to identify attacks patterns and group them in honey nets. It is extremely important to use a clustering methods and similarity measure that best groups the available data. The honey net, part of which is shown on the slide, is a multi-level set of intelligent honeypots that continuously monitor the network. The important property of this honey net is the ability to track attacks and detect their patterns. This process includes 3 stages: collection data and selection features, determining similarity measures suitable for pattern detection, and grouping of similar patterns. That is clustering. The first step involves extracting features that represent the relevant characteristics of malicious actions from the data. Data collected by the honeynet and data obtained from their analysis include characteristics like the number of malicious sources per time unit, the number of packets received per time unit, the volume of data received per time unit, etc. Clustering data changed over time is complicated due to the opacity of the similarity measure and implicit nature of the relationship between time series. So, time series transformation into a feature space suitable for correct clustering is required. We propose to perform preprocessing of time series on the basis of the neural network recurrent autoencoder. It allows using unlabeled dataset and unsupervised learning. Due to this preprocessing, it is possible to use different similarity measures for k-means clustering. The autoencoder consists of the recurrent encoder and recurrent decoder. The output of the recurrent encoder allows it to receive feature representation of time series obtained from the honeynet. The recurrent encoder and decoder consist of a convolutional unit and a recurrent unit. The convolutional unit includes convolutional layers, batch normalization, and max pooling by time axis, and is intended for preprocessing data for recurrent layers. The recurrent unit is a stack of LSTM layers with residual connections. The property of LSTM neural network is an effective processing of the features of time series. Residual connections are used to catch time dependence and to avoid vanishing or exploding gradients during autoencoder training. The loss function for the autoencoder training consists of 2 components: the loss function of reconstruction by the decoder and the loss function for k-means clustering. It is proposed to use the loss function suitable for the regression problem, in particular mean squared error, mean absolute error, Huber loss, and logarithm of the hyperbolic cosine loss. The k-means clustering loss is calculated on the basis of the similarity measures. The proposed similarity measures are Euclidean distance, Pearson correlation coefficient, Mahalanobis distance, and the distance obtained by the dynamic time wrapping algorithm. The clustering procedure includes a few steps. The first step is collection and preprocessing data, including actually data collection by the honeynet, selection of time window duration, and scaling. The second step is training of the recurrent autoencoder, which consists of 2 stages: initial training and tuning. The initial training involves training the model with considering only one component of a loss function, a reconstruction decoder loss function. Tuning is performed taking into account 2 components, both a decoder loss function and a clustering loss function with one of the similarity measures. The next step is receiving feature representation of the honeynet data with the recurrent encoder. And the last step is a pure k-means clustering procedure, which provides the operations. Calculate the k-means clustering algorithm for different cluster quantity values. Calculate the integral criterion of distance between objects within clusters for each number of clusters. Selection for the set of calculated integral criteria, the minimum one, and corresponding to it the number of clusters and the set of centroids. The analysis was conducted on the basis of data received from the HoneyNet. It is shown an initial and a clustered fragment of multidimensional time series representing HoneyNet data. Clustering was performed using different combinations of a decoder reconstruction loss function and the clustering similarity measure. The results were compared to the pre-labeled patterns and are shown on the slide. The best results among similarity measures are shown by dynamic time warping distance, which is quite logical since this distance is more invariant to some displacement compared to the similarity measures. So the information provided by the HoneyNet with corresponding analysis allows monitoring malicious actions, clustering them, obtaining patterns of attacks, and therefore increases the security of the computer network in general. Thank you for your attention.
Thank you, Antonina. Colleagues, do you have any questions?
What kind of data use in these experiments?
We use the data obtained from HoneyNet, which consists of 8 honeypots, and then we form time series of certain features for this data.
And another question, why do you use the HoneyNet?
What do you mean why we use the HoneyNet?
No, maybe another network will be better.
HoneyNet, in this context, HoneyNet means the network of honeypots. So I think in this context, we don't have any alternatives because we use some set of honeypots.
I understand.
Thank you for the question.
Thank you.
Thank you. So, colleagues, any questions? No? Thank you. Thank you, everyone, for interesting presentations, for interesting questions. And now our session is ended. And I'd like to invite you after coffee break, the next section, evaluation. Thank you. Have a rest. Bye-bye.
Сергій, ще одна презентація.
Excuse me.
Михайло Косянчук, Ігор Якименко.
Thank you.
От Степан Івасів є.
But in my program, okay, excuse me. Okay.
Last page of program.
I see. Okay. Are you ready? Excuse me.
Yes, I think so.
Okay.
Good morning. You see my screen?
Yes, everything's okay.
Yes, thank you. The paper name, the same bit module formation of residual number system for application in asymmetric cryptography. Speaker Stepan Ivasiv, Western Ukrainian National University. Nowadays, the rapid progress in information technology area, in particular in mission critical application, leads to the new demands for improved reliability, performance, and productivity of various computer systems. However, existing approaches and methods for data transmission and precision and operate in a positional number system cannot actually increase requirements data processing reliability without reducing the performance of computer systems with limited hardware and economic resource. Let's consider positive pairwise
coprime integers P1, P2, and Pz, which are called base of system model. Let's define P. This RNS is non-positional system in which the non-negative integer n can be presented as a set of non-negative residues from division of this number on the chosen basis of the system, such as 1. The reserve conversion into a positional number system is usually based on the Chinese remainder theorem, as shown in second, where P element should be calculated as shown in 3. One of the options to simply procedure. One of the options to simply procedure is used different form of RNS. The factorization method, suppose Z plus 2 model PZ and PZ are unknown. Mathematical calculation leads to the following expression, as shown in 6. After substituting 7 into 6 and performing some mathematical transformation, we get the conditions that must be satisfied to determine MPF RNS model set of any capacity with 2 unknown models, as shown in 8. Therefore, the left part 8 should be factorized, and the parameters A and B are determined based on it. Additionally, as a result of 8, the model Pz and Pz minus 1 should be integrated integers, shown in 9. The figure 1 shows the graphical dependencies of the model P4 on the values of model P2 and P3. As we can see, the absolute value P4 increase with increasing of P2 and P3 at P1 equal minus 131. Integer values of parameters P2 and P3, P4 create a model system that satisfies the condition of MPF RNS. For model MPF RNS after replacement of P2, P3, P4 equal A, B, C minus P1 and corresponding mathematical transformation, formula 10, is converted to the following expression as shown in 11. We get the conditions that must be satisfied to create MPF RNS as shown in 12. The calculation shows that in the vast majority of cases, following equality must be used to satisfy condition 12 as shown in 14. For example, let's consider MPF RNS, which consists of 4 modules. In this case, conditions 7 and 9 will be as shown in 15. All possible operations for system with model for MPF RNS, which with P1 equal 8 and P2 equal minus 9 and calculation range are presented in table 1 for 5,185 and table 2 for produce 5,183. And the table 3 represent possible options for set of 4 8-bit models for building MPF RNS. Table 4 presents the produce for finding model with the same bit size, 7 bits, to form the MPF RNS. In this research, the methods of 4 model sets of the same bit size creation in a modified perfect form of residual number system are development. This allows using the bit grid registers for more efficiently. This problem is relevant for usage in asymmetric cryptography and noise protection coding algorithms. Thank you for your attention.
Thank you, Stepan.
Have you any question?
Colleagues, questions, please.
Anatoly Melnik, please explain in more detail where you plan to use the result of this work.
The result of this paper, building the same bit size model formation of residual number system, it will be implemented for asymmetric crypto system and everywhere where you using RNS system, because it's very lower hardware computation and with using the RNS system, and you can use less hardware components when you can use the same bit models for formation residual number system.
I understand. Thank you.
Okay, thank you. Colleagues, any questions? No. And another notion is that due to some obstacles of communication failure, Volodymyr Mukhrun and their team will make their presentation on the next section. So for now, our sections exactly is ended. Thank you for your attention. Thank you for presentation and questions. Now we have a coffee break. See you in 30 minutes. Bye-bye.
Bye.
Thank you.